Thanks for that introduction. Yeah, so I will talk about some work which we put out in December last year. It's actually been ongoing for a long time, but we were confused about certain things, which I will get to. But we finally finished it. And it's based on some earlier work that goes back 2017 and also 10 years ago, where we did similar things for higher supersymmetry and lower loops. All right, so what are the ingredients that I'm going to talk about today? One major part of this story is color kinematics duality. I'm not going to review it. I'm going to just introduce it whenever I need it. Another part of this talk is going to be double copy for pure gravities, so pure supergravities. Let's put super in parentheses. Pure, I just mean that there's only one multiplet, the graviton multiplet, and no matter besides the whatever matter is in the multiplet. A third topic that I'm going to talk about today is SUSY decomposition. Which I will get to exactly what that entails, especially at higher loops. I will also talk about dim-reg, which is a tricky topic in the context of super n=1 super Yang-Mills. Specifically, the aspect I'm going to talk about is mu terms. How do we define them for n=1 series? And that's going to take me to the territory of massive Spinor-Helicity. And also massive on-shell superspace. And I'm going to assume that there is some prior knowledge of the massless case. So I'm not going to review that. Also, I should say that in this talk, I'm not going to talk about doing integrals, so no integration. I could have added a reference where we do the two-loop n=2 integration, but I guess I will not talk about it here. All right, so that's what I'm going to try to cover. And they're all connected in that we're trying to solve this problem of finding two-loop amplitudes, and we're led through all of this. But let me take one step back and give what is the real motivation. So the real motivation is that we want to study UV properties for lower supersymmetric, so n less or equal to 4 supergravities. Specifically, we want to study pure supergravities because they're more constrained in the sense that we only have to look at amplitudes involving external gravitons or graviton multiplets, and then we know the UV properties of the amplitude at the given loop order that we're studying. Now this is a tricky subject because it's a very complicated series, and the less supersymmetry actually makes it more complicated because then you have less tools to use. We all know how to compute in maximal supersymmetric series, but when we go below 4, it gets trickier and trickier. Yep. Yep. Yes. Well, so first of all, you can ask, what can we learn from one loop? And one loop we cannot learn much because everything is finite in 4 dimensions. You can go to higher dimension and study, when is the first place where certain theories diverge. But let's stick to 4 for now. So then you go to 2 loops and you check what happens at 2 loop, and it turns out that all supergravities are also finite at 2 loop, right? So you have to climb to 3 loops if you want to find a divergence. I'm going to talk about 2 loops today, so I'm not going to get to UV divergences in this talk. I could also go to higher loops, in higher dimension at 2 loops. So that's one of the motivations actually. So that's actually why I want to do Dimmerig. Basically, I just want to compute where I can and check if there's a UV divergence or not. And this could depend on loop order and dimension typically, right? And the number of supersymmetries, yeah. So that's what I mean by study. Yeah. Higher? Well, so if you have higher supersymmetry, then you have to go to higher loops. Yeah. So so for n equals 4 and higher, there has been calculations all the way. 4 loops has been done for n equals 4, and 5, and so on, and I guess there are current efforts at 5 loops for n equals 5. And we know that if we want to study n equals 8, we actually have to go to 7 loops. So yeah, this is, I'm somehow, that's also an interesting direction, but that's really, have to climb very high loop orders. So I'm just saying, let's study the lower supersymmetric ones where we can do it at more modest loop orders, right? Yeah. Some of the techniques that I'm going to introduce here today are overkill if you want to study larger than 4, right? So I'm going to focus on the aspects which are tricky when you go less supersymmetry, right? All right, so as I said, going less than equals 4, this makes it tricky to compute, and we need efficient method. So specifically, what I will use today is the double copy, but with a ghost. So I will talk about it shortly why. So with ghosts. And well, let me talk about now why I need ghosts. So specifically, if you look at some tensor product of the states, so let's look at the vector polarizations in Yang-Mills, and you look at the decomposition, you get that you can write it as something like, looks like the, let me also put a bar here, and forget about the tensor product. Well, let me write the tensor product. So you have this plus the symmetric one, let me write it like that, and then you have minus something, let me write this eta mu nu over d minus 2. You have something like this, antisymmetrized, and also half. And then you have something like this, d minus 2. So this decomposition here is basically into the symmetric traceless part, the antisymmetric part, and the trace. And this we can identify as being the graviton. This is essentially in 4 dimension, we just call it the axion. In d dimension, it would be some b mu nu tensor field. This here is the dilaton. So the problem is when you do double copies, that's typically you get polluted by these extra states. if you just think of helicities, we know that there's 2 helicities in Yang-Mills, and then you double copy it with 2 helicities, and then you get this identity, of course, that 2 times 2 is equal to 2 plus 2. So this is the extra states that we don't want, axion and dilaton, and we need to get rid of them. When we're above n equals 4, it turns out that those states are actually just part of the graviton multiplet, so we don't need to worry about it. But when we go below n equals 4, we need to remove these states, and that's why we need some prescription that removes them, and that's essentially a ghost prescription. Let me give you an example. So if I want to compute a one-loop amplitude in GR, I will have to look at some diagrams. For example, let's say I do 4 points, so I will have my favorite box integral. And if I try to construct my box diagram from double copy, I would first compute this thing in Yang-Mills, and then I would square it. There's other diagrams, but let's just focus on this diagram. But this obviously does not give the right states, because in the loop here, I will have all the states. I will have the 2 graviton states and the dilaton axion states propagating. So somehow I need to get rid of them. And it turns out that there's a convenient prescription, and that is to compute a diagram which involves a fermion. And then double copy that one separately, and then subtract it from that. And what I mean here by this vertical bar, I just mean that you have to multiply this diagram times the chiral conjugate, so the one where the arrows go the other direction, right? So you can compute this and check that indeed, if you have color kinematic satisfying diagrams, you can just compute the square of this one times this chiral conjugate, and the factor 2 here just means that you have 2 states that you're removing, and that actually gives the right gravitational amplitude. And you can generalize this to supersymmetry. So if I want to do some supergravity, you do the same thing here. You put some super Yang-Mills here. You square that. Well, sometimes it's not a square, but let's assume for simplicity it's a square. And then what you need to do is that you need to compute a matter contribution. Typically, it has some chirality associated to it, so you also take a square like this, where you flip the arrow. And that also works. Yeah. Yes. Yes. Why it works? Yes. Yeah, so it essentially works because I think it's actually easiest to understand it for the n equals 2 case. So if you do n equals 2 supergravity, then it turns out that you can generalize this formula. So, so you add, and then you add NF, NF states, let's call it NF. And maybe there's a factor 2 as well. So it turns out that this is also a valid double copy that you can do. And I should point out that in this case, this is like a hyper times a scalar, say. Yeah, let me do it properly. So you multiply by another diagram, which has the opposite direction, and that could just be a scalar. And that's how you get n equals 2. And also you have to do n equals 2 super Yang-Mills times n equals 0 Yang-Mills. And it turns out that this is actually, this amplitude here is part of a family, and it's called, what is it called? It's called the Luciani model. I don't know if you know Luciani. I don't even dare to spell his name, Luciani model. or Luciani family. So it's a family of vector multiplets coupled to gravity. It's basically the vector multiplets minimally coupled to supergravity, n equals 2 supergravity, and this is part of this family. So now, and I put an F here, but the number of states, the number of vectors, so the number of vectors is really 2 plus 2nf. So you see that if I actually plug in -1 here, I get 0 vectors. So that's kind of the trick, that this is part of a whole family, and it doesn't really matter what numbers I plug in here. I'm always going to be in that family. And if I plug in a negative number here, I'm just go, one step backwards in this family, continuous family. And that's one way to see that it works. I think that's my best reason why it works, yeah. Yep. Well, I think here it's just part of some minimally coupled matter. It doesn't have a name. But the point is that when you have supersymmetry, all the supergravities are classified and they're well understood. So that's why yeah. You can also do this for more supersymmetry, but then it's basically you get that's a unique theory, which is basically the minimally coupled vector and so on, right there. Sorry, this is actually a scalar. Sorry, this is a chiral multiplet. Sorry. Yeah, sorry. If you flip the sign here, you get the vector, the Luciani model. But there's also you can couple hypermultiplets as well. Anyhow, yeah, I wasn't planning to talk about that. But the point is that you're putting in a negative number here, and that can also have an interpretation as adding ghost to the theory, right? Just like Faraday-Popov ghost, you have to put in a minus sign for each closed loop. Okay. All right. So yeah, so essentially from this what we learn is that we need to compute like the pure Yang-Mills, pure super Yang-Mills, and we need to compute the matter graphs as well in this series. Now there's another reason why we want to compute matter graphs, and that's SUSY decomposition. So this goes back to work by Byrne, Dixon, Kosover, maybe Dunbar as well. So 93, 94. And the idea here is that, we don't need to compute in each theory, like each theory that we do, we don't have to do the computation anew. We can recycle stuff. So for example, if we want to compute n equals 2 super Yang-Mills amplitudes, then what we can do is that we can start from n equals 4 super Yang-Mills. Let me again just draw one diagram as an example. So we can start from n equals 4 super Yang-Mills, and then we can subtract the unwanted matter again. So we subtract 2 hypers in this case. So these are n equals 2 hypers. And then we get the right states for n equals 2 super Yang-Mills, the pure super Yang-Mills case. And we can do the same thing if we want to, for example, do n equals 1 super Yang-Mills. Again, we start from maybe the same graph. We know that n equals 4 is very simple, so we start from n equals 4, and then we subtract 3 hypers. Now you might complain that that doesn't look like n equals 1, but it turns out that if you put chiral multiplets in the joint, then typically they add up to hypermultiplet. And so therefore, this is actually gives the right answer. Now, if you put the chiral multiplet in some fundamental representation, this identity is not there. But on the other hand, that also leads to chiral anomalies. So that's why we typically don't care about such graphs. So let me actually write this second identity in a different way. So we can also think of A n equals 1 super-Young-Mills as starting from n equals 2. So we can also start from n equals 2 super-Young-Mills. And then we just subtract two chiral multiplets. So n equals 1. Right. So you see that in this way of writing it, this identity here are basically the same type of identity as here, right? So you start from the theory which has more supersymmetry, and then you subtract the matter content appropriate for the theory you want, right? No, so you can easily convince yourself that at one loop it holds for all the diagrams. I'm just drawing the box because, well, later on I will only need a box, but it's also more convenient, yeah. So it holds for all. I mean, obviously, diagram by diagram, it does not hold because each individual diagram are not gauge invariant. But once you sum over all diagrams, since this identity is just a linear operation on your diagrams, this will also hold for the amplitude, yeah. Yeah, so that's what I will come to. I will also then extend it to 2 loops. But it gets a bit trickier at 2 loops. So here you could easily have written the identity just in terms of partial amplitudes, like color-ordered amplitudes. At 2 loops, that's harder. I think you could probably do it, but it's a bit harder to see how it works. So at 2 loops, I will also use diagrams to do it. Yeah, but essentially, I'm just doing linear operations on diagrams. And so those linear operations you can map to the partial amplitude as well. Okay, so this is how I get the pure super-Young-Mills. But let's say I want to get some matter, so I want to get a hyper. There's also relations for those. So for example, I can decompose my hyper. So n equals 2 hyper in terms of n equals 1 chiral multiplets. And now I actually have to be careful because chiral multiplets are really chiral, so I actually need to add an arrow. So I have this one, so n equals 1 chiral, and then I have to add the conjugate diagram. So n equals 1 chiral. So basically, yeah, you know, the hyper is essentially just a sum of these 2 diagrams. Now, I could also, of course, take in the difference. Minus. That's certainly not something which has n equals 2 supersymmetry. This has still n equals 1 supersymmetry. So I'm just going to call like the odd n equals 1 chiral. And by odd, I mean that this is actually odd under parity. This is actually even under parity. This is odd under parity. Obviously, the multiplet is the same. It's just the way it interacts is slightly different. Now, this is also n equals 1 chiral. Now, usually we don't care about this one because this one is actually related to the anomaly. So it's related to the triangle anomaly. Obviously, I wrote a box, but if you do this for triangles, you're going to get the triangle anomaly. Or the chiral anomaly. So usually we ignore those kind of diagrams. All right. That's SUSY decomposition. Essentially, it's a slight rewriting of how it was done in the 90s, but I will generalize it to 2 loops. I think. Let's see if I actually wrote notes about that. Yeah. Ask me when I get there. But before that, let's talk about color kinematics duality. So the reason why I only keep drawing the box is because the box is all I need. So when I use color kinematics duality, then I can always relate my triangle. So I have a triangle that looks like this. I can always write that as a difference of 2 boxes. Now I should say that here, before I was talking about the full diagram, like the numerator and the propagator, but this is strictly just for the numerator, so I should have written the numerator of this graph, the numerator of this graph, and the numerator of this graph, but often I will not do that because it's sort of cluttering the graphs too much. So let me stop doing that. It's clear from the context when I'm referring to the numerator and when I'm referring to the full graph. Another diagram that you really want at one loop is the bubble graph. So that one can also be related to the triangle through a Jacobi relation, kinematic Jacobi relation. Let's see. Right, so basically you permute these 2 legs here and subtract them. That gives the bubble. One thing you have to do here is you have to be very careful with your loop momenta that you line it up, because this is it's basically a functional relation on the numerator as a function of L, right? So you have to keep track of where L is sitting. And you can also do this when you have matter graphs. So let me draw a matter graph. So if I have matter in my triangle, on the outside, I'm always going to have my gluons or gravitons in the case of gravity, or I'm going to have the supersymmetric partner. So always going to be the vector multiplet in this case. But inside, I'm going to have different multiplets, so that's why solid lines are my matter. Right. So it looks identical to the Jacobi up here. And again, you have to keep track of L. Okay, so you see now, I can always map back everything to the box. Like the triangle maps to the box. The bubble maps to the triangle, but the triangle in turn maps to the box. And this also holds if you're interested in any other diagram at 4-point. But these are the diagrams that actually gives you something when you integrate them. Okay, so yeah, so to summarize, if I use my SUSY decomposition and I use color kinematics duality, I can essentially reduce all my work to a set of masters. So this is color kinematics duality plus SUSY decomposition. And one of this graph is going to be my box for n equals 4 super Yang-Mills. The other graph is going to be my box with a hyper, so n equals 2 hyper. And lastly, one more graph that I'm going to need is my parity odd chiral multiplet. So this is n equals 1 chiral, but odd. So from these identities here, luckily I haven't erased them. You can see that I can always start from n equals 4 and get other things. But okay, I did erase some of the diagrams that I needed. Essentially, the hyper is here. It is here. Then I also had the identity that two chiral multiplets, if you sum them with a plus sign, it actually adds up to the hyper, right? So this actually captures the even part of the chiral multiplet, and this captures the odd part. Now, I did say that this one gives the anomaly. Once you use the Jacobi on this one, it gives you a triangle, and that triangle is going to be anomalous. So you might ask, why do I even care about this one? Well, it turns out that when I do supergravity and I double copy this graph, it actually does contribute. It contributes with a non-zero result and something which is no longer anomalous, which is interesting. Okay, let me just do a recap what these things are. So this numerator here, so I'm going to only care about the numerator. This is something probably quite well familiar. So I can write it as this. Delta 8q. So this is the supersymmetric factor, and this is just some helicity factor that gets the helicity weights, right? So I'm assuming I'm scattering vector multiplets here. I can also write up what this guy is. So maybe I do that. Let's see, can I fit it? So that's this guy. This guy here. Let me write it up, and then I'm going to define what these things are. So this is kappa 1, 2 plus kappa 3, 4 s minus ls squared 2s squared. Okay, it's not a full answer, but let me stop here and explain what this kappa. So these are kappas, not k. It's just my poor handwriting. So what is kappa? Let me erase this one because I'm not going to need it. So kappa basically just keeps track of which legs have a minus multiplet. So when I do n equals 2, I have a chiral multiplet for the vector and an anti-chiral. So this is just keeping track of it. And the way I do it is essentially I'm writing down something very similar to this. So let me do it. So it's 1, 2, 3, 4. Again, this is just to get the helicity weights correct. And then I need a supersymmetric delta function. In this case, since I have reduced supersymmetry, it's 2 times the number of supersymmetries. And then I'm also multiplying by a helicity factor, which is I, J, to the power 4 minus calligraphic n. And then let me also add some extra parameters here. This is just so I can well, let me explain also that my vector multiplet, we call it V, n, is a sum of two terms. Is one which has like a, let me call it, has plus helicity. Then there's one which has negative helicity. And I just multiply that by some auxiliary parameter, theta. So specifically, for n equals 1, this theta is a Grassmann-Odd parameter. So this is what my kappa are. They basically just keep track of which leg has a plus multiplet, which one has a negative multiplet. And maybe I should also define what let me call it, so v n equals, let's say n equals 2 plus, so this is just the gluon plus a fermion, something like this, plus a scalar. And v n equals 2 minus is then phi bar lambda minus a eta a, and then eta squared a minus. My signs might be off, but hopefully that doesn't bother you. This is the n equals 2 multiplets, and if you want to have the n equals 1, you just cross out the scalar, and you cross out one of the fermions. That gives you the n equals 1. All right, so I said I didn't finish this formula. Also, maybe I should specify that, well, never mind what this is. But there's some additional terms here. So first of all, there is a Levi-Civita. So 1, 2, 3, L. You might say that that's parity odd. No, it's not, because there's also a prefactor here, which is a difference of kappa. So this is kappa 1, 3 minus kappa 1, 4. So when you do well, maybe it's parity odd. It does not violate CPT, that's for sure, because this is CPT odd, this is CPT odd. Over u squared. Finally, there's one more term, so this is what I wanted to get to. So that's a mu term. So this is when you do dim reg, you need to introduce mu terms. And it looks like this, plus perms. Okay, good. So this is the numerator. You might be surprised why I call it numerator, because you see that obviously it has some denominators. But this is due to the fact that I'm trying to make supersymmetry manifest. So I can make supersymmetry manifest at the expense of some non-localities. So you already see that there's some non-locality here, but there's also a non-locality here, and it's correlated with the helicity choices, right? So you can basically think when I have minus minus here, there's a non-locality in the S channel. When I have minus minus here, there's a non-locality in the U channel. But in the end of the day, these non-localities will not, they're not correct. They will give the right amplitude at the end of the day. So yeah, they're not spurious either. They're just sort of, I have absorbed certain terms into the box just to make supersymmetry manifest. All right. Any questions? You might be wondering when I'm going to get to 2 loops, but hopefully I will get there. Okay. Am I writing too small, by the way? It's fine, or yeah. All right. So, okay. So let's talk about the mu term here, right? So mu term here is just the extra dimensional part of the loop momenta. My loop momenta is basically some 4D part plus, well, sorry, let me not use mu there, nu. Right, so I'm decomposing my loop momenta into a 4D loop momenta plus an extra dimensional part, and that's the mu that appears here. Yeah. Yeah. Yes. Yes. Um, yeah, I think this is the only way to make it manifest. So I mean, you could of course just write, you know, the gluon amplitude and then a fermion amplitude and then a scalar amplitude. Yeah, but if you want them all packaged into one object, I mean, you have to write down the delta. You have to write down this, and then already writing down this forces you to have this non-locality, right? But then. Well, it's possible that you could have gotten away with less of these denominators, because some of them could also be imposed by the fact that they satisfy color kinematics duality. That's extra constraints. Maybe that, but you can also check that, you know, when you do your cuts, you typically have such terms. I think what you could have done is you could have moved them. You can move them over to the triangle or to the bubble, right? In fact, you see that it's s squared, so you could guess that that could have maybe be absorbed by the bubble, right? Yeah, so I think it's not just SUSY. This is definitely SUSY, but this is also maybe color kinematics duality and power counting constraint that I'm imposing. Yeah. Okay, so let's talk about this mu term here. So first of all, I just call it mu because, well, it doesn't matter where in the loop it's inserted. I did indicate where L is sitting. It's sitting here. Yeah. So one thing here is that, as I said, first of all, how do I compute this mu term here? Well, so the way I do it is that I actually go to 6 dimensions, and then I can compute in n equals 1 in 6 dimensions, and that's equivalent to this theory upon dimensional reduction. So that's actually how I computed this one. But I should also say that, as I said, that this diagram here actually is the parity even part of, it's a parity even part of the n equals 1 Carroll multiplet. So in fact, this also provides a dimensional regularization prescription for n equals 1. And that's kind of strange, because if you know anything about Dimrig and SUSY, you know that they don't actually go very well together. But you know, magically somehow here, n equals 1 super Yang-Mills is now well-defined in Dimreg. Now, by now I mean for this one loop 4 point. Right. In general, this is not true. I mean, n equals 1 is always badly defined when you talk about Dimreg, or yeah, they don't go well together. But here, you know, it's a big exclamation mark. Somehow it worked for some mysterious reason, right? Now, yeah. Why? Well, here you can say it's an accident. It's an accident because this diagram is secretly n equals 2. I mean, it's both n equals 1. This is also like n equals n equals 1 Carol, or 2 times n equals 1 Carol. So you can say it's just an accident, right? But what we want to do is we want to take this accident and see how far we can go. You know, can we go to 2 loop? You know, and that's part of, yeah, that's where we'll get into the later part of this talk. So one issue here is, of course, is that the parity odd Carol, so the odd one, this one you cannot uplift it, and that's precisely why it's anomalous, right? I mean, if there was a way to uplift it to higher dimension, it would not be anomalous, but it is. So this is not defined in DIMReg. But usually people don't care because it's an anomaly, so you just simply do not consider series which have this anomalous term, right? But it turns out, as I said earlier, we actually need it in the double copy. It does actually give something. So yeah, so usually dropped. But for double copy, we need it. Need it. It actually contributes. It gives non-zero contribution. Well, also in gauge theory gives non-zero contribution, but it's anomalous. But it gives non-zero contribution, which is not anomalous. And the reason for that is that the anomaly has to do with its parity properties, or the fact that there's a Levi-Civita. But if you take 2 copies of it, those parity properties are fine, and you can uplift the Levi-Civita to a gram determinant instead, right? So that's why it actually contributes to gravity. But again, I mean, how do we deal with mu terms if you want to introduce mu terms? So it turns out that if you just parameterize your ignorance, so parameterize ignorance in the mu terms. Basically, what I mean is that you write down an ansatz for what this diagram should be. You have no way to check what the correct answer is, but you write down anything you think is reasonable. Then it turns out that when you do the double copy, it will drop out. So what I mean here is that the extra terms that I'm adding to this diagram with an ansatz, they drop out in the double copy, right? The extra mu terms. The things that are not mu terms, they will contribute. So that's good news, right? Because I have no way to fix what these mu terms are, but it doesn't matter, it turns out. So that's the good news. And then we hope that things are going to be similar when we go to higher loops, which is not guaranteed. Okay. I should also mention, how do we know that we get the right answer when we do the double copy? Well, the reason is that there's actually 2 ways to do the double copy. So one of them is to do, let's say we take n equals 1 super Yang-Mills, and we double copy it with n equals 1 super Yang-Mills. That's one way, but it turns out that this is essentially the same thing as taking n equals 2 super Yang-Mills and double copy that with pure Yang-Mills. There is a slight difference. The slight difference is that there's some extra matter multiplets that differs. But we can always control that. We can always subtract out those matter multiplets. And then you can actually check that these two double copies gives the same answer. And now, since this is n equals 2, we can actually uplift this to 60, because we can do n equals 1 and 60, and we can do Young-Mills and 60. And then we can check that that double copy exactly matches what we computed for n equals 1. I don't have the n equals 1. Well, I don't have this one. But you know, what we compute for this guy and for the even one, it actually works. So everything is consistent. Okay. Okay. So I'm basically down here now. So I have discussed dimreg and mu terms, and then I will repeat. I mean, I have done the basic stuff. I will repeat it a little bit when I get to 2 loops. But maybe one step before 2 loops is, let me also say a little bit more about how we construct these numerators. So one constraint that we put is power counting. Yeah, sorry for my spelling. So let me do the box again as an illustrative example. So my numerator of the box, sorry, this is not number supersymmetry. This is my numerator. So my numerator, I'm basically going to say that I allow it to have a certain number of loop momenta. Typically, I allow it to have 4 powers, but then I have to subtract the number of supersymmetries. So calligraphic n. So for example, if you do n equals 4 super Young-Mills, you know that the box diagram has no loop momentum in its numerator. It's just a scalar box. Same thing if I do the triangle. I'm going to allow 3 powers in the non-supersymmetric case, and then if I have supersymmetry, I simply just subtract the number of supersymmetries. And if this number go negative, that just means that I do not have the diagram. And the same thing if I do a bubble, I'm going to say that I'm allowing 2 powers minus the number of supersymmetries. So in particular, if I do n equals 2 super Young-Mills, all my bubbles are going to have no loop momentum in them, in the numerator. And I can continue that. I can also do tadpoles. So tadpoles, they will have 1 power minus n. So that means that in n equals 2 super Young-Mills, I don't expect to have tadpoles. Now there's, at 2 loops, there is one diagram which has a tadpole, but so that seems to, sometimes there's some exceptions, but in general, this seems to be the rule that I impose. So this is basically the 1 loop counting, but I can always think of 2 loop diagrams of having a sub-diagram, which a box, triangle, bubble, and tadpole, and do the same. All right. Yeah, then I should also say that we also impose crossing or maybe permutation symmetry. On our graphs. Obviously, if I have 2 graphs and they only differ by external labels, I just say, oh, they're just related by permutation. But there's also other symmetries. For example, I can mirror the graph when I impose that as a symmetry. So more generally is basically graph symmetries. Graph symmetries. So maybe let me just give one example, which is maybe the more interesting. So the box diagram has a dihedral symmetry, which means that I can just rotate it. So obviously that diagram is the same as this diagram, which is just I just rotate it. And that actually is a constraint that I impose on my numerators. So this means that my numerator in the ordering 1, 2, 3, 4, comma L this numerator is equal to my numerator in the, what is it? So 4, 1, 2, 3. And then here you have to be careful. So here L refers to this leg. So I should still refer to this leg. But the correct way, this is always confusing, but the correct way is to write down a shifted loop momentum here. So for example, that would be P4, I guess, yeah. So this, yeah, you can convince yourself that Feynman diagrams respects this symmetry. So that's why I also want to impose that on numerators. Okay, all right, so now I'm ready to go to 2 loops. So let's discuss 2 loops. Obviously, I have only half an hour, so this is going to go a bit quicker. Okay. So when I discussed one loop, I said that I had 3 masters, which was essentially the n=4 box, the n=2 hyper-multiplet box, and the n=1 parity odd Carroll box. At 2 loops, I'm going to also find that there's a certain number of masters. So let me begin by writing down the masters. At 2 loops. So I'm going to do this the quick and dirty way. I'm just going to give the answer. And the answer assumes that I have used a whole bunch of identities, color kinematics duality, supersymmetric decomposition, and other identities, but I will get to them. First, I'll write down what the masters are. So one of my master is the double box in n=4 superangles. That's one of my masters. You probably know what it is. It's very simple. Then I have n=2. So this is n=2. So n=2 superangles. But now I put a hyper in the outer loop. And then I put a vector multiplet here and also externally. I'm only going to consider external vector multiplet. I already said that, but let me repeat it. I also need to allow a hyper in the left loop. So this is still n=2. So this is hyper. Also this. All right, so you might be surprised that I'm only writing on double boxes, but there are other graphs. So there is this graph. Now let's see if I can draw it. So this is it's terrible drawing. So I guess normally would call it maybe a triangle pentagon or pentatriangle. Yeah, pentatriangle. And again, this is also n=2 superangles with a hyper in the outer loop. All right, so yeah, that's not so many more. So there's only 2 more. So this is n=1 superangles. And now everything on the inside is actually chiral matter. So this is chiral matter. And it turns out that this is actually the even part. I'm only going to discuss the even part, so I don't even need to put arrows here, actually. This is chiral matter. Everything is chiral matter, this and that. And lastly, I have this. This is my last diagram, which is also a pentatriangle. also n equals 1. And yeah, the caveat here is I'm only going to do even chiral multiples, even contribution. The reason is that we got tired, so we decided to only focus on this part. Yeah. Yes. Right. Think of it that I'm always gonna. My chiral multiplet n equals 1. I'm always gonna think of it as a superposition of the plus and then the minus. Yeah, so then, yeah, just use this identity everywhere, and then, and some of the vertices will not make sense, but that just means that it's 0, yeah. And in some sense, this is, yeah, it's equivalent to n equals 2 hyper, but the interactions will not respect that. So the diagrams only has n equals 1 supersymmetry, not n equals 2. Yeah. Oh yeah. No, definitely. You could do various things. We picked these ones because we like them. So yeah. So how do we pick them? Well, specifically, whenever we have vector multiplets, we want to increase the supersymmetry as much as we can. So that's why we picked n equals 4 for this one. We could have picked n equals 2 vectors or n equals 1 vector. That would also be fine. But obviously, as much supersymmetry as possible. And likewise here, when we have a single matter line, then we pick n equals 2 because we know that such contributions exist in n equals 2. When we have like 3 matter lines here, then there's no choice, but there has to be n equals 1 because this type of interaction doesn't exist in n equals 2, right? So that's the general philosophy, is that we try to crank up supersymmetry as much as possible, and then we're led to this. You might also say, why didn't you write down like the non-planar, like the non-planar boxes and so on? And well, they're related by Jacobi relations, right? There might also be some assumption about some diagrams being 0. For example, we know that this diagram is 0 in n equals 4 and so on. But anyhow, these are the non-zero diagrams that we need. And let me give you one example. So it turns out that I can also write down n equals 2 answer, which is actually simpler. For some reason, 2 loop is simpler than 1 loop, which is the first time I've seen that. So I can write down this diagram in n equals 2. So it's actually, it's the same kappas that I used before. So this just denotes which multiplet I'm looking at, which vector multiplet. So this is the numerator I'm writing down. And this is a chiral trace, gamma matrix trace. That turns out to be the whole numerator for this n equals 2 double box. Yeah, so somehow, originally we didn't write it like that, but then later on somebody realized that you could reassemble it to this chiral trace. And this actually, this chiral trace has appeared in some other work. I think there was some work by, was it by Nima or by Jake or something, where they're considering double boxes with these numerators, because they're simpler when you do integrals and so on. Anyhow, and you see that there's some mu terms. So this is L1. This is sorry, L2. This is simply the dot product of the mu term in this loop and the mu term in the other loop. It's very simple. All right. Now let me focus on n equals 1. So if we want to get n equals 1, we need to compute this once. And we want to do it in dimreg. So let me get back to dimreg. And the amazing thing here is that we only need disk graphs, but they involve actually no gluons in the loop, right? Only involves matter. So the idea here is that instead of introducing mu terms, which we cannot introduce mu terms in n equals 1, but we can introduce mass terms. So we can, like, make the matter massive. Because often masses and extra dimensional momenta are kind of related. And then, yeah, so the idea is that then we can get 60 kinematics by introducing masses. Now we actually need more than one mass. We need also the complex conjugate of the mass. So the reason for that is that we're trying to describe 2 extra dimensions. So that means that I need something which has 2 components. So I'm gonna think of it as m and m bar, and then my invariant mass is simply m times m bar. Basically, I'm just using complex coordinates in some 2-dimensional internal space. Also, we have to be careful that if we wanna take this interpretation, we have to impose mass conservation. Because we know that if we want to think of loop momentum as being in 60, then there should be some momentum conservation in 60, so we have to impose mass conservation. All right, and you can ask, how do you do that? Well, it's easy to take your n equals 1 super-Yang-Mills Lagrangian, and then just add some mass terms to it. So you just add a deformation of mass terms. So what are those mass terms? So let me write down what they are. So first of all, that's just a kinetic term, but let me write it for good measure. Yeah, so let's introduce some SU2 indices, which are just SU2 left indices. Let's see. Okay, so we have spinors, psi tilde. These are the dotted ones. So basically, we have a different mass term for the chiral and antichiral, or left-handed and right-handed spinors. Then for the scalar, we just have m bar, phi bar. Sorry, maybe I should use the capital or this one. And lastly, there's also a deformation to the interaction. In order to preserve supersymmetry, we need to write down this interaction, phi bar, phi bar, and then plus the complex conjugate. So that's, sorry, now I'm using the wrong phi, sorry. Okay. Now we want to have multiple matter multiplets, so let me also put a flavor index. Let's call it A. So that also go on the mass, because the mass can be different for the different flavors. What I do here, I'm gonna now make them interact, and I'm gonna choose the Levi-Civita A, B, C, A, B, C. In principle, I could have picked any tensor in flavor space, which has 3 indices, but I pick it to be antisymmetric, because then I can just put a trace of the color. So the color is just a trace here. So I'm obviously going to get FABC and then epsilon ABC. So it's going to, symmetries are going to work out. All right, so that's the deformation to my Lagrangian. I'm assuming that you know what the n=1 is, the undeformed one. You might worry that this complex mass is like something you can undo by making some changing the phases of the field or something like that. Like sometimes when you have a complex mass, it's just a phase that you can remove by a field of a definition. But here I believe the answer is that no, you cannot, because when we compute amplitudes, we definitely get dependence on the phase, at least before integration. So that has a real physical consequence. Okay, so now since I have masses, I need to work a bit harder on my notation and my supersymmetry, because I need to basically introduce massive amplitudes. So let's consider some massive Spinor-Helicity. I'm probably running out of time, yes. So maybe I do that kind of quickly. So it's convenient to write some massive momenta as a superposition of massless ones, so we can write it as follows. Sorry, M bar, let's call it R, a reference momenta, and then R dot K, factor 2. So I can write like 2 massless momenta superposed like this is going to give something which p squared is equal to m squared. And using Spinor-Helicity, I can do the same thing. So I can write my p alpha dot in terms of the k spinors and also in terms of the r spinors. Okay. And that leads me to introduce this spinors, which has, sorry, let me continue. So I can also write that as P, A, where this sum here is just taken care of by this little group index A. So this is SU2, little group. And I can just write that as R, K spinors, and M over K dot R, and P A square. It's also a column vector. Okay, good. So now I have defined my spinors. They depend on this complex mass. Obviously, there's some choice. I could have just put the m bar here and m here, but this seemed to work. And And now, since I'm doing supersymmetry, I also should introduce massive supersymmetry. You might say that I don't need it because my external states are still going to be massless, but I still need to do unitarity cuts. So I need to know what the amplitudes are on it, when I do the cuts. So massive SUSY. So I'm going to introduce some supercharge. Well, I'm going to introduce this notation here. So Qi is simply my massive spinors, where I have contracted the index with an eta. So eta is my Grassmann odd parameter, and it has the SU2 index. I just contracted, and so this is my definition of Qi. We used Gothic Q in our paper, but I cannot write a Gothic Q, so there should be a Gothic Q. And likewise for the square spinor. Sorry, it's I, A, eta, A. And there's also an index I for the particle label. Okay, so now what I can do, I can take this and I construct my supercharges. So the supercharges are simply the sum of all the particles and this Qi. So this is basically the individual supercharge. And I can also construct Q dagger, which actually is an integral d eta squared of the angle spinor. Okay, you can check that the commutation relation is now holds for supersymmetry. Yeah, so this should be equal to sigma alpha alpha dot total momenta, and then the other commutators are 0. Okay. And I can write down amplitudes with this delta function of the supersymmetry. I didn't define it before, but now I maybe need to define it because it's probably less familiar. So simply, it's a sum over I, j, and these spinors. If you would write it in massless notation, it would look essentially the same. The 1/2 here is just because of overcounting. The minus sign, I think, is just a convention. Maybe we got it wrong somewhere. Okay, having defined that, let me write down some amplitudes. Let me write down the Yang-Mills amplitude for 2 chiral multiplets and a vector multiplet. So this is n equals 1. And this is a plus helicity vector multiplet. So this amplitude is some x factor times delta to q. And what is the x factor? This is the x factor that Nima and friends introduced, which we can actually write. We can write it as epsilon 3 plus times p1 over m1. This is particle 1. Let me put 1, 2, 3. You can also write it various other ways, but this is the one that Nima and Yutin and company introduced. I can write down the opposite helicity. Still n equals 1. This one is slightly trickier. So it's 1 over 2xm delta 2q. And then some weird factor here, 2m bar eta 3, 1 plus 3 q1 plus 3q2. Oh, it looks a bit weird, but you can show that this is actually just related to the conjugate delta function, also with an eta 3, 1. Sorry. So by this I mean this is the Fourier transform of the CPT conjugate. Like so, yeah. It's a bit weird, but 3-point amplitude is always a bit weird. That's why this extra eta is put in there. And there's also 1 over x here. Okay, lastly, let me write down what if I have 3 chiral multiplet. Now, strictly speaking, I should put in my flavor index also AB, ABC. So there's an epsilon ABC, delta to Q. There's a 1. The first term is 1. And then the next one is a little bit weird as well. Okay. So you see here things depend on the chiral mass and the conjugate mass, right? So things depend on this. It looks a bit weird. It looks a bit non-crossing symmetric, but 3-point is just weird. So this formula is the correct formula. Am I out of time? Yeah. Maybe 5 minutes more? Yes. Well, maybe I should ask for more than 5. Okay. Yeah, so one thing I want you to do is I want to write down an expression for this diagram. So this diagram, so this is chiral multiplet, and this is a vector multiplet. Yep. 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 Yes. This is the whole. Yeah. Yeah, it's 3 level, yeah. Usually there's a denominator, but usually there's an angle bracket, whatever denominator, but you see that this x here is a bit non-local, right? Yeah. Yeah. But this amplitude is strictly local. There's nothing, well, okay, there's an m there, so yeah. Yeah, I mean 3-point is supposed to be local, so yeah. So, but anyhow, so here, now I'm gonna write, well, let me write down the full diagram, right? So you might know that this diagram is actually a gauge invariant by itself, so let me just write down this diagram. So what is it? Q1, Q3 plus Q2, Q4 minus Q1, Q2. Q4. Okay, that's the full answer. So in this case, supersymmetry does not cause any non-localities. I mean, the only non-locality is, of course, just the pole, which should be there. But otherwise, it's very simple. Let me also write down this. So this is only hypers everywhere. Sorry, chiral multiple. So not hypers, chiral. This one looks like, first of all, if I have some labels, let's call 1, 2, 3, 4. This also should be labeled here. Also A, B, C, D. Here's just a Kronecker delta, but let me not write down the A, B, E, C, D. Well, let me also put here delta AB, delta CD. So that's the contraction of the Levi-Civita. And then there's a delta 2Q. Sorry, I'm getting ahead of myself. There's a pole. So in principle, I can make this pole massive, so let me make it massive. Yeah, that's my mass. This is my invariant mass, not the individual. And this is particle 5. That's why I have a 5 there. So there's M5 here, delta 2Q minus M5 bar, delta 2Q bar. This is just the CPT conjugate of each other. And then we have delta 2Q, Q1, Q2, Q3, Q4, minus M1, eta 2 squared, minus M2, eta 1 squared, minus M3, eta 3 squared, minus M4, eta 3 squared. Okay, there we go. Sorry. That's the numerator. All right, that's the numerator, that's the pole. Now, the reason I wrote them down is because now you see that they're actually kind of similar. That this here is very similar to this here, right? And in fact, that's not an accident. There's actually an identity satisfied here. So the identity is the following: that if I take that diagram and then I subtract this other diagram, actually I think I labeled them incorrectly. Yes, this is T, so this is 2, 2, 3, 4, 1. So if I take, sorry, this thing here is equal to that minus that. You can check that the numerator here is equal to 2 of these numerators, but with permuted legs. Basically, this factor gives that, and then the other permuted guy gives that, and all the other terms cancel out. But there's more. I can also do this one individually. So if I only do the vector contribution, that's also equal to this following kinematic Jacobi identity. Sorry, this is vector now. So this is a this is a chiral multiplet, and this is a vector. Right, so just inspecting this, you can show that these two identities hold. And the reason why I'm showing that is because in addition to imposing the usual color kinematics duality and the usual SUSY decomposition, we also impose this bonus, we call them bonus relations. Bonus kinematic. And they're bonus because, first of all, they actually don't hold in general. They only hold when you have 3 or 1, either 1 or 3 flavors. But if you have any other number, then they don't hold. Also, you don't really need them because each of these diagrams is actually gauge invariant. So if you want to do double copy, you know, you can just do it. There's no ambiguity in what they are. It turns out that this is actually related to n equals 1 star. So if you have n equals 4 and you make 3 chiral multiplets massive, then you get n equals 1. And so that's precisely the situation here. So this is n equals 4 plus 3 masses. I think that's the definition of n equals 1 star. We were struggling a bit if the other case, so we called it n equals 1 double star, which is basically n equals 2 plus 1 mass. I don't know if it has a better name. I don't know if you know. But these are the two cases which are very special. Anyhow, so we imposed those additional bonus relations in order to get to our masters, which I now have erased. And then you might ask, what about supersymmetry decomposition? Well, it's essentially as straightforward as it is at one loop once you write it down in terms of diagram, so I'm not even bother to write it down. You just think of these multiplets as being superpositions, and then you just do decomposition in the most naive way. I was going to talk about the problem, but I think I'm really out of time, so maybe I skip the problem. There is a little bit of tension. Yeah, there is a little bit of tension between SUSY and DIMREG still, and the issue is that when we do this unitarity cut, so basically we cut all the exposed lines, but we leave a blob here. Then naively we would expect it to be a sum of these two diagrams. So also I picked the same flavor, then you have these two diagrams. So the double box with a vector exchange and the double triangle or the bow tie with a vector exchange. These are the only two diagrams that contribute. But it turns out that the cut doesn't quite work, meaning that the cut doesn't fit what we put into our Lagrangian. There's an extra term, and the extra term looks like 2m bar, I think it is. Kappa 1, 2 plus kappa 3, 4 over S. And this is 1, 2, 3, 4. So there's a problem here that this specific cut doesn't hold for our solution. And there's this leftover piece here. Now, because the way I wrote it, it looks like it should belong to the double triangle because it has an S-pole. But that's not super clear because recall that all of our numerators are a bit non-local. So it's not super clear that this is the double triangle. But if it's probably correct that it is the double triangle. And if you interpret it, you can actually figure out that it's actually this diagram. You can actually do the maximal cut and expose this diagram. But now this is actually not a massive multiplet because you see there's no mass there. This is actually like some kind of, let's call it extra dimensional vector multiplet. It's actually a gluon in this case because they cannot be a fermion, so this is actually gluon. I wonder if that's the signal. But so the point is that we didn't put this particle into our Lagrangian, and that's why it didn't match, right? But so maybe we should have put it in. So what we did is we went back and we decided that we can maybe violate some of our cuts with mu terms because this is basically a mu term. And then we find a slightly deformed solution which works, but it has kind of an interesting feature that it doesn't only deform this guy, but it pretty much deforms every diagram that we have, but in a very special way. So typically every diagram that has this topology, so imagine I just shrink the external leg to 0. All of the diagrams which has this topology will get a new contribution, which is mu1, 2, so mu1 plus mu1, 2 plus mu2, 2. This is just the dot product of, this is mu1, and this is mu2. So every diagram gets this dot product of this mu, this is what this means, in this specific combination. And any diagram which has the topology of a barbell will get mu1, 1 plus mu2, 2, where this is mu1 and mu2. So there's a very specific deformation of all our diagrams. And the interpretation that I make of this is that we actually need to put some extra states. And these extra states, they only live in an extra dimension. So they don't actually see the external legs. They only see the loop legs and not the external legs. And that's why they are such a uniform deformation of all the diagrams. Anyhow, so that's the end of the story. We found a solution for n equals 1 where we had to take some extra step, deforming it a little bit. You can say that, are we allowed to do that? Well, DimReg is always ambiguous at two loops because there's scheme dependence. There's always scheme dependence at two loops, so we can associate it with certain scheme. And so we were happy with it, and we put it out after a long delay. Anyhow, I think that's all I'm going to say, so thanks. So if you actually want to see the answer, you have to go to the paper, because it's too long to write down, yeah. Say again? Yeah. No, so we put out what we had. It satisfies all the four-dimensional cuts, so therefore it's a valid n equals 1 integrand, because that's basically the best you can do. The reason why we're obsessing about the mu terms, this actually caused like a 3-year delay in putting out the paper because of this issue. We're obsessing about it is because if you don't get them right, the double copy will not work in higher dimensions, right? Which we want it to work because we want to check UV divergence in 5 dimensions or 6 dimensions of n equals 2 supergravity. So you might ask, okay, did you get the double copy to work? And the answer is that we're not yet there because we only constructed the parity even diagrams. Well, I erased them, but so we only constructed the diagrams where we have no arrow. So we also need to construct the odd ones, which they're independent, but we just ran out of steam, so that's going to be the next paper, I guess, yeah. So unless we have those diagrams, we cannot do the double copy properly, yeah. Practical running of the workshop, Henrik and Olivia, and I think we should give them a big hand for that.